Today's program, we are going to be talking now about storage in the context of mining. This is like a super hot topic. It has been talked about for many, many years, but only few companies have managed to crack that industry and to actually deliver projects for mining companies. And we are very lucky today to have one of them with Francois de Jager from CrossBoundary Energy. I'll give you a quick introduction about Francois. He's the senior engineering manager at CrossBoundary and is responsible for technical support of hybrid generation projects. Brings with him 10 years of experience in power system engineering for projects ranging from mining, industrial, and utility applications. And before CrossBoundary, he's worked also on the consulting side with Orecon and Zutari. Francois, I'm very, very pleased to welcome you today. Are you with us?
I am, thank you, John.
Yes, wonderful. We can see you, we can hear you. What I'll do is I will give you the controls. This is done so that you can start sharing your presentation.
Let me just enable that.
Yes, and then just move on presentation mode. Perfect. Over to you, Francois.
Excellent. All right. Yeah, thank you for this opportunity, everybody. Like John said, we're presenting a case study for BESS in mining, and specifically BESS in microgrids specifically. So just as a quick intro to CrossBoundary Energy, we are a pre-financed independent power producer. We develop, own, and operate various distributed renewable and hybrid power systems throughout Africa. We currently have a fairly large portfolio of microgrid projects in West Africa as well as Southern Africa, specifically Madagascar, which is also the projects that I will be focusing on here. And I think throughout the life cycles of these projects, we've learned that it's absolutely critical to develop an understanding of the complexities behind not just the technical aspects, but also with regards to supply of equipment, logistics, ESG, regulatory aspects, etc. And in that regard, we've grown our teams to cover those specific complexities within our projects. And dealing with microgrids, I think as a power systems engineer, it's something that's very close to my heart because it's a very unique aspect. Every project has a unique request from clients and a unique responsibility for us to manage the grid in an efficient and safe way. And in that, we've also found that partnering with the correct EPCs and suppliers also gets us a long way in terms of implementing more robust, more unique systems, and not just something right off the mill, right off the shelf. And then also, it's obviously important that we always keep optimizing our systems. I think, as the previous presenters have noted, there's always room to get higher renewable penetration, to push a bit for lower carbon or for more carbon reduction, etc. So just as an intro to the project that I'll be presenting, it is a project that we did for Rio Tinto. It was commissioned about mid last year. The location is in Madagascar, which posed its own logistical challenges and a lot of additional effort needed to go into to manage those aspects of the project. It composes of an 8.2 megawatt 1C base solution. We also installed an 8 megawatt peak solar PV plant, which all integrated within the existing microgrid, which was powered previously by a 24 megawatt HFO plant. So, like I said, as being a power systems engineer, this presentation will definitely be a bit more technical and focused on the power system aspects and challenges that we faced and had to overcome within this project, and that we found very interesting. And I think there's a lot of use cases in other projects. So just to understand the layout of the system, we essentially had the mine process plant, which is 95% of the load, sitting on one end of the system. We had a 33 kV existing distribution line, which feeds the town and the port. And we essentially installed the solar PV, 8 megawatt solar PV system on the other side of this distribution line due to land availability, etc. So during this case study, I'll not be solely focusing on the energy arbitrage, etc. use cases for this project, but rather on the additional ancillary support services that the BESS can provide within microgrids. And that's absolutely critical that we have additional support within grids to manage power quality, manage stability, and ensure that we, at the end of the day, have a reliable to handle a lot of trips or dips in power, etc. So looking through the specific applications we deployed here, I split it into essentially generator support functions and grid support functions. Some of these will be well known, some of these are a bit more unique. So on the genset side, we implemented ramp rate control on the renewable facility. We implemented reserve power support, or rather genset starting deferral applications. We looked at optimizing the genset operation point and very critical reactive power balancing. On the grid support functions, we implemented a fast frequency response application on the battery. We applied a very novel approach to dynamic voltage support, and which also allowed us to defer, distribution infrastructure. And we applied a harmonic current damping application as well. So diving specifically into the ramp rate control and some data that we collected during the commissioning exercises, it's essential that we apply this ramp rate control application within microgrids and weak grids in general, looking at the intermittency of solar. If we all of a sudden have a cloud cover going over our plant and we lose the bulk of our solar PV, we could sit with decaying frequency or rate of change of frequency that falls beyond what the grid can handle, and we can very quickly see a grid collapse if our solar penetration was reaching levels above what our genset step change can handle. Excuse me. So the way that we essentially tested the robustness of this application was by forcibly removing about 2 megawatts of solar PV during operation and allowing the battery to respond and ensure that the ramp rate was limited to 60 kilowatt per second. Now, the reason I showed the network at the start was just to understand the complexity behind this application, actually, because we didn't go with a co-located solar PV and BESS system, of which the reason I'll get into a bit later. So what this means was during a loss of PV, we had to ensure fast enough communication between the 2 points in the network, which is about 16 kilometers apart, which entailed the installation of a fast fiber ADSS link to allow our battery system or battery control system to respond within 500 milliseconds and inject the same 2 megawatt of power that had been lost and curtail then at a slower ramp rate. As we can see in the graphic, our generator was then able to slowly ramp up and not see the step change that was actually happening in the system. Another critical application that we applied was on the reserve power support and genset operating point efficiency management. So when we look at a microgrid, obviously the number of generators that's required is impacted by the system loading, obviously the renewable generation at the specific time, as well as the spinning reserve power required, which is a very critical aspect and which also reduces efficiency because you end up running more gensets than required because for the possibility of possibly losing a generator or sitting with curtailed renewable operation or possibility of an increased load for whichever reason. So the online generator loading needs to be managed so that we can ensure an optimized fuel efficiency and not run an additional generator just for the sake of reserve. and also to maximize renewable penetration. Because if we have too many generators online, obviously the amount of renewable generation we can inject into the system is also limited by the minimum loading of the gensets online. So managing the operation point of the generators increases the efficiency and also extends the asset lifespan. So what we ended up implementing was essentially a maximum loading limitation on the gensets, which we set to about 85% of the nominal capacity of the generators. And by implementing this functionality, we were able to defer starting of additional gensets during the day. So I don't know if you can see my cursor here, but essentially if we look at conditions at about 10 o'clock here, we could see the solar PV. I chose a day that was very intermittent in terms of irradiation. Solar PV dipped by about 4 megawatt, and our gensets had to take up some of the additional capacity, and the base immediately responded, injecting about 4 megawatts to ensure that the loading of the gensets does not exceed 85%, which allowed us to ride through that intermittent portion of the day. And once solar PV increased or generation increased again, we were able to decrease the amount of active power injected by the battery, allowing us to not start that genset. Because obviously you don't want to go starting gensets every couple hours. That's also not great for the lifespan of the gen, and you're increasing maintenance activity, etc., which doesn't bode well for an efficient system. Further than that, what we also applied was state of charge management, or rather charge management, from our renewable generation. And what we ended up applying was to allow the solar PV to charge the battery once our generators reaches a point of 65% operation, which is still in its high efficiency ranges. So what that entails is once our solar PV injection reaches levels where the generator is sitting at 65%, we start charging the battery and keep that operation point at 65%. And only once full state of charge has been achieved by the battery do we then further reduce the operation point down to 50% of the genset. And if our renewable penetration or the load drops, allowing us to, or rather not allowing us to inject as much solar PV, only then do we start to curtail the solar PV plant in order to maintain the minimum loading on our generators at 50%. So yeah, another critical aspect that we had to implement in this microgrid was the fast frequency response within the battery system. So don't want to go into too much of the of the definitions here, but essentially fast frequency response is a primary control response function that's implemented within the base inverters. So the reason I say that is it's not a secondary control response that is sent by the energy management system, which would lead to delays in response. It is something that's inherently set up within the battery system as a power frequency droop curve to allow very fast response from the battery in case of frequency deviations outside of the expected deadband. Obviously, this is a fairly tricky application to test or assess. So what we ended up applying is to create a dip in frequency within the system by tripping one of the generators, forcing the e-stop, which led to a loss of 1.8 megawatt on the system. This entailed a drop in frequency down to 49.35 hertz, which required the battery system to respond. So just looking at the theoretical or the expected fast frequency response here, if I just use my cursor here, if we look at the point FM, which is essentially to where the frequency dipped to, We can see we're in the injection range of our fast frequency response. And if we apply the mathematical formula of the amount of active power that we were expecting at this point along our droop curve, we could see that we calculated to about 1.615 megawatt that was required to be injected by the battery system at a dip of 49.35 hertz. And if we then compare this theoretical response with the actual performance, we could see that within that 500 millisecond, which is just the measurement resolution that we're looking at here, the battery system immediately injected an offset of 1.615 megawatt, which is exactly what we expected from the system. And I guess the test was seen as successful because the frequency collapse was arrested, the system recovered successfully, and no load shedding scheme was actually, all load shedding schemes was deferred, and the power supply remained online. The load shedding scheme was active after 48 hertz after 1 second, so we recovered the system well within that time. So yeah, like I said, one of the more novel approaches that we had to apply on the system was managing the flow of power across the 33 kV distribution system that I showed at the start of the presentation. So if you've worked on distribution systems before, you would understand that there's obviously a thermal limitation when it comes to the actual conductor ratings, but there's also typically something more critical, which is the voltage collapse point, which is essentially caused by the flow of reactive power through a reactance. In other words, if we try and push reactive power across an overhead line with more inductive capacity than capacitance, we end up with a large voltage drop, which ends up collapsing the system if we exceed the vulnerability limits. So at the early stages of this project, we obviously performed a lot of power system studies and identified this as a major challenge that we needed to correctly address. So when looking at the theoretical voltage drop across this overhead line, what's important to consider is the impact of power factor, or the impact of the amount of reactive power that you're trying to send across this overhead line. If we look at the graphic that I'm showing here, the green line represents the operation at about 0.98 power factor. And as we move up, the power factor gets worse, and the voltage drop across the line also increases to about 10% at 18 megawatt for a power factor of 0.79, which was the typical power factor of the mine at the time of installation. So in order to ensure that we didn't need to upgrade this entire line, what we needed to manage was the amount of reactive power that's actually flowing over the line. And considering that it is only the solar PV plant that's injecting across this line, what we ended up doing is ensuring that we set a fixed power factor control mode on the solar PV plant and limit the power factor to 0.98 at all times. So if we now compare what the theory told us versus the actual volt drop measurements across the overhead line, we can see that we are pretty much spot on in terms of our representation of the overhead line parameters within our analytical models. You'll see there's a slight negative measurement in some cases. This would be during the night when the power flows in the reverse direction across the line. So what this entailed was we were able to defer the upgrade of the line by reducing the amount of reactive power that's being transferred across the line, and rather keeping the solar PV at a fixed power factor. But this comes with other challenges. So with solar PV limited to a power factor of 0.98, there's obviously a balance of reactive power that needs to be supplied, considering we're sitting with a load that is operating at a power factor of about between 0.79 and 0.9. And if we consider no BESS application at the moment, then essentially the generators would need to be providing this additional reactive power. And what this would essentially imply was that our gensets would be moving away from the efficient operating point down to being overexcited, which could lead to less efficient operation or possible damages to your alternator in the long run. So the approach that we applied in order to ensure that we can manage the flow of reactive power across the overhead line while balancing the reactive power supplied by the generators was to essentially apply a dynamic reactive power support functionality, which considers the amount of active power that the solar PV is injecting, the amount of active power that the BESS is injecting or being charged with, and match this with the actual power factor of the load, which is the same power factor that the gensets are seeing. Apologies, this is getting a bit complex, but this was a very interesting part of this project to ensure that we always have sufficient reactive power online and that we are not overcompensating or overexciting any of our assets. And if we look at the graphic here, what we can see is the combined reactive power supplied by the PV and battery essentially matched the power factor of the generators. If you look at the top here, which is exactly what we tried to achieve, which ensured that we always operate our generators within the most efficient point, giving us the best fuel efficiency at any moment in time. And then finally, the last application we applied was harmonic current damping. And why is this important in microgrids? I think it's important to understand that, first of all microgrids will have various sources of harmonics, whether it be VSDs or motor drives, etc., because we always need to manage the amount of startup current or inrush current within these systems, because we don't have the advantage of utility that can just quickly inject high levels of power to start up a large mill or motor. So having these VSDs on the system would always cause a harmonic current to be on the system. And the challenge with integrating renewable generation within microgrids is that essentially what we're trying to achieve is to reduce diesel generation or HFO generation. And by doing that, we're actually removing gensets from the system, which entails reduces the fault level or the system strength of the system. And the less fault level we have, the higher becomes the linear harmonic impedance of the network. So again, sorry if it's getting overly complex, but what I'm trying to say is the less generators you have, the higher your impedance of the network. And if we apply Ohm's law, if we have a higher impedance, it doesn't take a lot of harmonic current for us to sit with very high levels of voltage distortion in the system, compared to a system that's only supplied by diesel generation. So what we applied on the base inverters themselves was to tune our harmonic current damping functionality to ensure that we address the critical harmonics that was present on the system before we connected our battery system. And if you look at the graphic to the right, I think it's very apparent that before we were sitting with a very high fifth harmonic current in the system, and after we applied the harmonic current damping, we were able to reduce that to within acceptable levels, even when operating with less generators online. And yeah, that is my story. So just a shout out and thanks to all our valued partners who contributed to this amazing project, and just a nice snip of the Madagascan coast with our 8 megawatt PV projects. Yeah, thanks, John. That is it from my side.
Thank you very much. Great presentation. Impressive how how far complexity can get. This was already briefly mentioned in our first presentation, but here you've obviously really pushed the topic and the analysis very far, which is great. Thank you very much. And it's indeed a beautiful project. I have a few questions for you. First question is a bit of a vocabulary question. You've mentioned multiple times microgrids. In the African context, there is another term which is recurring a lot, which is mini grids. Sometimes both get a bit confusing. Could you please explain what you understand under microgrids, just to make sure we're on the same page?
Sure. I mean, I guess there's a lot of various ways to look at it, but my definition would be a microgrid is essentially a high voltage system, medium voltage system that is just disconnected from the main grid. So I know the way that European countries and Americans look at microgrids is essentially a utility that's able to split up into various systems and resynchronize again. So I guess that would be the end goal, end state where we want to end up, is to have a distributed grid that's able to split up and resynchronize. And that's essentially my definition of a microgrid, whereas a mini grid is definitely on the smaller scale side. So looking at typically low voltage distribution systems with residential customers and not really a lot of industrial or mining loads.
Very clear. Question from Momo about fast frequency response. Is this 500 millisecond fast frequency response a typical standard for this kind of projects, or is it a threshold that you have defined because of the specific needs of this project?
So a bit of both. There is guidance within the IEEE 1547 standard with regards to typical ranges that an off-grid system should respond in. But I think it's always going to be a nuance between the theory and practice, right? The challenge is you don't want to essentially respond too quickly and cause instability within the system. So it comes down to testing, assessing where the system is most suitable and where our recovery can be achieved most efficiently. But the 500 milliseconds, just want to emphasize that was just the metering resolution that we were looking at. The actual response on a fast frequency response would be within the microsecond range.
And we've got several questions on this topic of fast frequency response. Justin is asking, is this 500 milliseconds defined at the energy management system level, or is it configured at the battery inverter level?
So the fast frequency response is a primary response. In other words, it's sitting at the battery inverter itself. So the battery inverter sees the frequency deviation and immediately applies an offset. So let's take, for example, the energy management system was sending a continuous command of 2 megawatts to be dispatched by the battery system. Should the frequency dip and we expect to see an additional injection of 2 megawatts, the base system will essentially offset that and go to 4 megawatts. So it's something that sits on top of the EMS and the EMS doesn't have any control over this. Otherwise, we'd sit with additional communication delays, which we don't want there.
And then last question about fast frequency response, question from Carlo. Which type of batteries are suited for this? Are we talking about lithium batteries or are we talking about redox flow batteries?
So we applied this on LFP, so lithium iron phosphate battery systems. But important also to note that your injection of current isn't necessarily always linked to active power. It can consider reactive power as well, which is more sitting within your inverter itself. So yeah, I'm not getting into the technicalities as much, but if you have a DC bus that is energized, you can provide reactive power within the thermal range of your inverter at any time. And there's typically a bit of overload as well. So yeah, coming back to what batteries was, it's lithium-ion batteries, and I'm not sure honestly whether redox flow would be able to achieve those levels.
Moving on to the configuration of your system. So I don't remember the exact numbers, but roughly we were at 8 megawatt peak solar, 8 megawatt hours storage system. This is a bit different from many other projects where we see the storage component is 2x or 3x the PV capacity. Can you please explain why this was the chosen configuration?
Sure. Yeah, at the end of the day, it came down to the PPA tariff, but the application for this base for this specific phase wasn't actually as much on the energy management side, but rather on the power support side. Hence, we went with a 1C system and not a 0.5C or whatever increased storage capacity here. And also the reason we put it on the far end of the overhead line, which allowed us to ride through losses of our solar PV plant and keep the system online. So considering the size, 8 megawatt versus a load of 15 megawatt, there wasn't as much need to store additional power. As we move into future phases of this project, obviously that will become a component of as the oversupply increases to look at additional storage capacity.
Wonderful introduction for my next question. Thank you so much. In this project, we see that diesel is still very prevalent. Based on your analysis of how things are evolving on the solar, on the storage side of things, do you see a future where it would be possible to supply this spine with 100% solar and BESS? Or will diesel always need to be there? And if that's the case, why?
Depends who you're asking, right? So from our side, we are always pushing to achieve 100% penetration. It is a major challenge in projects like these. So first of all, considering it is a brownfields project, so we have existing infrastructure that had specifically been designed for a thermal power plant supplying the system. So in other words, your protection, your earthing, everything was done specifically around your thermal plant. So coming in from the side and going 100% renewable requires a lot of modifications within the network, within the control, within the protection aspects, which needs very careful consideration. Because obviously the fault level contribution from a genset is about between 8 to 12 times its rated capacity versus the battery can only achieve about 1.1 per unit of its rated capacity. So you really need to oversize the AC capacity of the battery to replace a genset fault contribution. But yeah, to answer your question, this is something we are actively looking into, and we're definitely pushing to achieve that within the coming years.
And then final question to you. This is maybe more a commercial slash financial question. But I know CrossBoundary has been doing amazing work on carbon emissions and carbon credits. In this case, thanks to the diesel reduction, this must also be quite important. Specifically in the mining industry, we know that international shareholders put a lot of pressure on this industry in particular to reduce emissions. Same question as what I asked in a previous session, like, are those savings already monetized somehow? Are they part of the overall financial calculation? Or is it just one metric that is there, but not yet really fully exploited in financial terms?
Yeah, so it is something that we consider within our financial models, but it's definitely not something we consider as let's call it as a real value add at this stage. I think the real value add at this stage is the reduction in emissions and the actual carbon reduction that the mine is seeing in terms of reduction in HFO usage. But in terms of carbon credits, I think this is still a growing market. Obviously not my area of expertise, but it is something we're considering in various projects as part of the requirements. So having these regs form part of the actual commercial structure.
All right, Francois, thank you so much. I see there were many more questions, but we need to move on to our next session. And if I did not get a chance to pick up your question from the list, don't worry, because these questions will be shared with Francois and his team, so he will be able to follow up with you later on and to address your specific question. Thank you once again for your time, and have a great day.